All right, and welcome everyone. Welcome to ARC Prize 2024 University Virtual Tour. My name is Greg Cameron, one of the co-leads of ARC Prize, and I'm very excited to be here with you today. For those that are just first joining us, ARC Prize is a $1 million competition to open source the solution to ARC AGI. Now, we started back in June, and the competition is just about to wrap up here in November, but we'll hear about that more in just a second here. Now, this month on the live university tour event, we visited over 1,500 different students and professors at 13 of the top USA AI programs. We want to first extend our gratitude to the students and the professors that helped us out today. They made an extraordinary event for us, and we're very, very grateful for that. So I'm excited to announce the two speakers that we're going to be seeing today. But before I do, I want to talk about a quick run of show. So what we'll be doing is first, we're going to hear from Mike and Francois about not only ARC Prize history, the competition, trends, but also Francois' opinion about how to maybe beat ARC AGI, which I'm very excited to hear about. And next, we're going to go into some structured Q&A. So for this, we're going to use Dory, which is a Q&A platform. And if you don't have the link, you can head over to arcprize.org/tour, where you're going to be able to get the link and go ask more questions from there. So to introduce our speakers, I first want to bring on Mike Knoop. So Mike is the co-founder of Zapier, where he led all of product and engineering before shifting focus to AI R&D in the summer of 2022. Next, we have Francois Cholet, who's the creator of Keras, the popular Python deep learning library, and the creator of ARC AGI. But that is enough for the introduction today. What I'd love to do is now pass it over to Mike Knoop, who can start us off today. Mike, about to bring you on.
All right. Hey, everyone. Thank you so much for being here with us today. Really excited to be sort of capstoning our university tour that we've been on for basically the last month or so. Hit maybe 16 or 17 universities all across the United States, and excited to show you a very similar talk that we gave to all those students as well. Reached over 1,500 folks. All right, let's dive in. So I'm going to start here today by telling you the story that I think we like to tell ourselves about the history of artificial intelligence. Basically, since the beginning of the field, researchers have sought to build these like AI systems by trying to leverage their human insight, their expert insight into sort of the nature of intelligence, the nature of the brain. And I think while this was the favored method, it was also really the pragmatic one for a long time because, you know, looking at this chart, just cheap compute did not exist yet until very recently. In fact, the cost of compute has been basically falling 2 orders of magnitude every decade, going all the way back since 1940. This is a really, really long-running trend. It's an important one. And finally, in the 2010s, and this was enabled by the sort of cheap abundance of GPUs, these deep learning methods finally started to work, right? From ImageNet to the Transformer, we started to see these general purpose search and learning methods that got applied to ever more impressive AI systems. You know, and all these sort of impossible domains that we thought were impossible for computers to do, like an image recognition or really complex games like Go or protein folding, self-driving cars, and of course, even language. This chart, I think, has doesn't seem like it has any chance of slowing down either over the next 10 years. And so one of the cool things you could do is actually use it to make predictions, right? In this case, you know, for predicting maybe the cost of what it might take to train a GPT-4 class model 10 years from now. Well, you know, 10 years ago, maybe $40 billion to train something if you were trying to train it in a month, you know, well within sort of the realm of nation states. And 10 years from now, you know, easily within the realm of, you know, just a basically modestly funded Series seed from a startup. I think language modeling turned out to be even more powerful than most researchers and practitioners expected. These large language models started kind of reaching human capability on basically every AI benchmark that we could like imagine and throw at these things. And I think importantly, progress on these benchmarks has been accelerating to date. The x-axis on this chart here is years since the benchmark was introduced, and it's been getting faster and faster. The slope of these lines is getting steeper and steeper. And so these like general purpose search and learning methods just empirically work. And I think that's why most people in the industry today believe that we'll be able to just continue to scale up this regime all the way to artificial general intelligence. I think we like to tell this story because it not only fits the data that we have over the last 10 years of deep learning progress, but it also fits the last 80 plus years of progress in scaling that price performance of compute. But I think this conclusion that deep learning can simply scale up to artificial general intelligence assumes a very specific definition of AGI. And I think that's one that's oriented around AI's skill as opposed to AI's ability to learn skill. In 2019, Francois Chollet published the ARC AGI benchmark, almost 5 years ago now. And this was a test to see, could AI systems efficiently learn skill and apply it to problems they've never seen before? And 5 years later, as of today, as we stand here and are here today, this benchmark still remains unbeaten. In fact, heading into June of this year when we launched ARC Prize, progress had even been decelerating. So what if scale is not all we need for AGI? I'm sure some of you listening today strongly believe in the scaling hypothesis. And I'm sure others of you listening, if you're here, may be fundamentally skeptical of it. And for the next half hour, I would just invite everyone here to sort of put on your curiosity hat as we sort of explore the ramifications to this question. So first, if you've this is the first time kind of tuning in or just passing by, just heard about ARC, you might be curious, like, what the heck is this benchmark? What has been so hard for AI to beat for the last 5 years? And I always think shows better than tell. So here's an example of one of the tasks that's in the ARC benchmark. It's kind of like an IQ test. And what you're given is a series of input and output examples. And your job is to find the pattern and then apply that pattern on the test that you're given. And so in this case, if we kind of stare at this for a minute or two, we might start noticing like, okay, it looks like what we're trying to do is figure out which of these red blobs do we turn blue? And how are we going to do that? Well, maybe we draw this horizontal connecting line between the left and right edge where there's a blue node, and a vertical line between the top and bottom where there's a blue dot, and wherever they intersect with a sort of red shape, we're going to color that in blue. And indeed, that is the rule for this particular test. You can apply it on the test input, and so you have to generalize a little bit. You actually have two horizontal lines in this case, but you're able to generalize by discovering the rule from the example pattern. The benchmark has hundreds of puzzles just like this one, with one unique thing, which is that every single benchmark looks different. Every single one is different. Every single one is unique. The only thing that they share in common, the main thing they share in common, is that every single one is designed to be very, very straightforward and easy for humans to recognize the patterns and recognize the answers. In fact, we have some human testing data from back when ARC first got created that suggested about 98% of the ARC private set could be solved by just one person, and with a set of 2 people, they got all 100 correct. But this stands in the face that today, no AI system can solve these puzzles. I think one really common misconception about ARC is that it's a visual benchmark. Certainly, we render it in a visual way for humans to sort of help make this social point that, hey, there is a task that's quite easy for you that is impossible for computers right now. But I actually think it's better to think of what ARC is as more of a programming benchmark than a visual benchmark. What you're doing fundamentally is trying to map a 2D array of numbers to another 2D array of numbers. This is what the actual screenshot of the JSON looks like in the underlying benchmark. And this is a pretty common thing you see in program synthesis research, where a very common test in that sort of research is to figure out how do you map a sequence of numbers to another sequence of numbers, and you're trying to discover a function that maps the two. And ARC merely extends that into the second dimension. You got a 2D array of numbers instead of just a 1D sequence of numbers. When I rediscovered the ARC benchmark a couple of years ago, I was pretty surprised it hadn't gotten beaten yet. I'd started looking into all these benchmarks from my time at Zapier, and I was sort of expecting ARC had been beaten, just like all these other ones that had been sort of rapidly reaching human capability. And so that got me curious. What makes this benchmark so special, so resilient? And I think there's a few things. I think the first, we said this before, every single task is novel and unique. And that means there's no really straightforward or easy way to cram for ARC. And this is really in direct contrast to how deep learning methods work as a paradigm, right? Deep learning works by putting more and more examples and situations into the models. Effectively, they're sort of memorizing answers and situations. ARC also only requires a handful of core knowledge priors to solve these tasks. You don't need world knowledge. You don't need facts on Wikipedia. All you need really is basic counting, basic integers, symmetry, rotation, reflection. These are experiences and skills that you likely acquire very, very early on in childhood development, between the first, couple years of age. Now, ARC does require you to be able to strongly and efficiently generalize from those core knowledge priors and compose them together to sort of solve these puzzles that you've never seen before. The private set, the state-of-the-art that we measure on, is a private set of 100 puzzles. This is another important aspect of the benchmark, and this helps ensure that nobody can overfit or just like contaminate on the answers or the solution paths. This increases our confidence, right? That like when someone reports a state-of-the-art, new state-of-the-art, we can sort of have a higher degree of confidence it's actually true progress. And then the last thing is that ARC requires efficiency. You get 2 guesses per task, and there's a limited amount of compute on the private set to an amount of time you get to sort of solve all 100. This helps try to mitigate the impact of techniques like brute force search. And I think brute force search is more of a better demonstration of skill, not a demonstration of intelligence, as we'll get into today. Unfortunately, up till the summer, ARC has been fairly obscure. I've been interviewing folks in sort of the Bay Area, at least, AI industry over the last couple of years. And maybe like 1 in 10 people that I had met had heard of this particular benchmark. And, I think that if ARC's durability now, 5 years in, suggests that we need some sort of new ideas, like some sort of conceptual progress towards AGI that we don't have yet today. Well, if that's true, like way more people should know this benchmark exists. In fact, it may be the most important benchmark in the entire world today. And so that's why this summer, Chalet and I decided to launch ARC Prize. It's this $1 million nonprofit competition to beat ARC and open source a solution. And I think we kind of would say, or like to think of it as this big grand experiment, right? To test this hypothesis on really the largest scale possible, which is, can frontier AI ideas beat ARC or not? One cool thing is we have a little bit of hindsight now, because we're 3.5 months into this contest. And so I think we can more confidently say the answer to that question is no. Frontier AI ideas today cannot beat ARC yet, right? This large prize helps like clear the space of all the low-hanging fruit ideas that I think researchers may have in their heads already. And I think this is now fairly strong evidence that we're missing something, maybe something pretty big, and maybe even as fundamental as deep learning itself. Since we launched, we have made progress. I think we're up maybe like 15, 20 percentage points now in state of the art. Really, really exciting. We're finally bending this curve in the right direction. It's cool to see ARC Prize has like catalyzed, I think, a lot of individual like folks that were working on it in the past to join, kind of like make super teams together and work on it together. A lot of the top teams are applying very similar techniques that we're seeing from DeepMind's AlphaProof and OpenAI's O1 model towards beating ARC. And unlike those systems, with DeepMind and AlphaProof and O1, where we kind of like just got blog posts from those labs, I think it's really cool. By the end of the year, we expect to have some open sourced code and approaches that emulate how those systems work, driven by ARC Prize. And while this progress, I think, is promising, we just crossed the 50% mark. I think we still do have a long way to go. We suspect that the last half of the benchmark is going to be really, really difficult to beat. Speaking of O1, OpenAI released this a handful of weeks ago. They called it their new reasoning model. They said that this was not just another language model. They said that this represents like an entirely new, maybe even scaling paradigm for AI. And when they launched it, there was like thousands of people on Twitter sort of asking like, okay, how does it do on ARC Prize? And so we tested it. And here's the result. O1 scores about double what GPT-4o scores, gets about 21% or pro, and it's on par with Claude 3.5 Sonnet. And even the new updated Claude 3.5 Sonnet, we just got that tested yesterday, and it's all these scores are pretty much still accurate from that. Now, I want to say, I think despite, it's kind of middling score here, especially relative to some of the sort of top scores from the sort of private and public leaderboards that we've got, I do think that O1 is not just another large language model, it's not just another iteration. I think it is the biggest genuine generalization improvement we've seen in a commercially available AI model, likely going all the way back to GPT-2, which came out also in 2019. And so I think you're going to see a lot more systems taking advantage of how O1 works. And so it's worth understanding, like, what is it doing? And O1 fully exploits this like chain of thought reasoning paradigm, or think step by step if you've done some prompt engineering with this. And it's doing it both at like a pre-training time and an inference time. At training time, at pre-training time, there's a model generating lots of synthetic chains of thought data, these like reasoning chains, likely over formal domains, things like code and math and theorem proving, things like this. And likely also, and this is somewhat speculative, but likely over informal domains too, maybe taking goals and breaking them down into sub-goals, getting human feedback to act as your reward function on the pre-trained side there. And then at test time, OpenAI says that they give O1 what they'll say additional time to think. And I think really what this is doing is instead of having O1 just spit out, one chain of thought and then using that to additionally ground a prompt to answer a question, they're giving O1 time to search over many different chains of thought, or maybe even backtrack over different chains of thought to find one that really works for the particular prompt the model is given. These charts work from the OpenAI blog post when they introduced it. And on the left side here, we've got a graph of this train time compute. It's on a log scale, both of these are, against accuracy on this AIME math benchmark. I think on the left side, this is kind of what we're used to seeing, right? This like log scale, the more examples and training data we put into the large language models, accuracy goes up. I think the really big news story here is on the test time side, though, on the right. Similarly, we're looking at a log scale on compute, and x-axis and the y-axis is accuracy on this. This is now a sort of log linear relationship between the more, let's say, time to think O1 is given at test time, you get improved accuracy, linearly improving accuracy. This makes reporting on O1 kind of tricky, actually. And I think this is going to be true for pretty much every AI system going forward, because I think they're all going to adopt things like what O1 is doing, right? Single benchmark scores are actually kind of deceiving going forward because OpenAI made a product decision, right? An arbitrary one or a business decision on how much compute to give O1 for every single prompt. Had they given O1 less time to think or less compute, scores would be worse on benchmarks. Or if they had given it more scores would be higher on benchmarks. This log linear relationship is, by the way, not the first time we'd actually seen this chart. We saw something very similar after we launched ArcPrize from this guy, Ryan Greenblatt, who's currently at the top of the public leaderboard. He wrote a solution that works like this. He's using GPT-4o. He's generating, I think, something like 2,000 Python programs for every single puzzle he gets exposed to, and then evaluating them and looking for a Python puzzle or Python program that solves the example input and outputs and then applies it on the test. Then he, I think, asked a really cool question, which is, well, how does performance of the system vary that I just made if I sort of vary the number of programs I sample? And maybe not 2,000, but maybe more like 16, 32, 64, and up. And he drew this graph. And he found this exact same log linear relationship between the amount of time he gives at test time to compute and accuracy on the y-axis. And I think fundamentally, you're going to see the same exponential scaling curve, right? This log linear relationship anywhere you're using combinatorial search or anywhere where your sort of algorithm has a fundamental O of x to the n complexity. You're going to see this kind of shape pop out. To beat ARC this way, you need to generate 100 million or more solution programs for every single task. And now the question is is that computable? And the answer is yes. Given a large enough data center, large enough amount of time and energy and money, you could do that. So have we beaten, have we gotten AGI then? And I'd say not quite. And I think for one reason is back in 2020, and remember, this is before any large language models really existed. There was the predecessor to ArcPrize ran on Kaggle. And all the solutions were using these hard-coded domain-specific languages with just brute force combinatorial search by composing together different transformations to look for answers. And the top score back then was only 20% by one team. However, after the initial Kaggle contest was over, they looked at the set of all of the solutions, and it turned out about half of the private test set got beaten by at least one of these brute force combinatorial search approaches. I think practicality often kind of rules out this O of x to the n complexity combinatorial search for AI systems. But even more importantly than that, I think fundamentally efficiency really matters for intelligence. I think it may have even been the hallmark that sort of was the gradient that evolution used to follow early organisms in terms of how they got more intelligent, right? They want to sort of evolve higher intelligence in order to expend less energy to navigate their environment or take less risk as they're trying to figure out which food they should eat. I think you can even see this yourself when you're taking ARC tasks, right? When you're looking at an ARC task, I think the language you would use is, oh, I'm trying to see potential answers. And then you're going to use some sort of system to sort of style thinking in your head to deterministically check them. And what you're not doing is generating, 100 million Python programs for every single task. So I'll wrap up my section here by summarizing, I think, O1 like this. I think O1 does represent a paradigm shift. I think it represents one of these paradigm shifts from, just memorizing answers, memorizing situations, to one of memorizing reasoning chains. But I don't think it's yet a broader departure from this paradigm of trying to improve model accuracy and model performance by just putting more and more examples and situations into the underlying pre-training distribution there. So all right, if LLMs can't beat ARC and O1 can't beat ARC, and none of the existing AI, sort of frontier AI ideas and approaches can beat ARC, what could? And to help answer that question, illuminate the future path forward here, I'm excited to introduce Francois Chalet.
Thank you, Mike. All right, so the million-dollar question is, how is this benchmark different from all the others? Why has it not been solved yet? And like Mike was saying, if you look at ArcGI tasks, they're not difficult, they're not complex, they're actually really straightforward for humans. And they don't require any special training, any special knowledge. They're all built on top of core knowledge, which any 5-year-old child has already mastered. And there's really just one thing, is that the benchmark is designed to resist memorization. So each task is unique. You must look at each task and figure it out on the fly. You cannot prepare for what's going to be in the benchmark. And over the past couple of years, there's been a lot of talk about how LLMs can do just that they can do in-context learning to adapt to problems they've not seen before. But if you look more closely, what seems to actually happen is that LLMs are fetching memorized programs that map to the current prompt. And if they don't have a memorized program ready, if they're faced with something that's actually novel, that's unfamiliar, even if it's very simple, they're going to fail. And that is so true that it's even true if the element of novelty comes in the form of a small variation on a problem that they did actually memorize. There are many, many examples of this besides, ARC itself. But here are a couple interesting examples to sort of ground this discussion. So first of all, you probably know about Caesar ciphers. So Caesar ciphers is a very basic form of encryption where you're moving the index of a letter by a fixed position. And LLMs can solve a Caesar cipher. And on its own, that is really impressive. But there's a catch. It only works for specific values of the key size, which are in fact the specific values that are found in examples of Caesar ciphers online. If you pick an unusual key size value, the model breaks down. And so that tells you that the model has no general understanding of what the Caesar cipher is or how to solve it. It has no ability to adapt to slight deviations compared to what it has memorized. Another interesting example that is very similar would be Alice in Wonderland type problems. So what you see here on the right. So an Alice in Wonderland type problem is a question of the form Alice has n brothers and m sisters. So how many sisters does Alice's brother have? So as a human, if you're looking at this question for the very first time, it doesn't take you too long to figure out that, well, the answer has got to be m plus 1. It's m, the number of sisters, plus Alice herself. And well, LLMs can in fact answer this question, but again, it only works for very specific values of m and n, the values that are commonly found online. If you try a range of different values, you will start seeing the model break down. And shockingly, this is even true if you vary the value of n, which is really surprising because the answer doesn't even depend on n. So the hypothesis here that you have to make is that LLM performance depends purely on task familiarity. So you can make an LLM do anything you want, no matter how complex, but only as long as you give it the opportunity to memorize the solution in advance. It's not going to be able to adapt to any kind of novelty, even if the novel problem is very simple, like in the case of ArcGI tasks, for instance. And to be clear, this is not just a limitation of LLM specifically. It's a limitation of any deep learning model. It's the entire curve fitting paradigm has this limitation. So a mental model that you can use to think about an LLM or really any kind of deep learning model is that you can think about it as a database of skill programs. So a skill program is basically just a function mapping a set of situations to the appropriate response for the situation. And an LLM is really just that, but covering many, many different skills and many, many different situations. And when you're training your LLM, you're training to predict what's next, given a token sequence. And in order to do that, it has to come up with vector functions, like vector programs, basically, that map patterns of input tokens to patterns of output tokens. And if your model had infinite memorization capacity, if it had infinite memory, it could encode these kinds of functions via a sort of lookup table that maps inputs to outputs. But of course, they don't have infinite memory. They only have a fixed number of parameters. And so as a result, what they're forced to do is that they're forced to compress the space of programs that they're memorizing. And they're doing that by expressing the new programs that they need in terms of bits and pieces of programs they've previously memorized. And this mechanism, this compression mechanism of program space is what forces LLMs to generalize a little bit, to be able to make sense of inputs that are not exactly what they've seen before, the way a lookup table would work, that are slightly different, but only slightly. This is what makes LLM useful, right? So anytime you're prompting an LLM, you can think of your prompt as being like a database query that retrieves one or more such programs and then applies them to your input. And this fact perfectly explains scaling laws. If you're measuring model performance just based on the score that you're getting on exam-style benchmarks, where the skill programs that you need can be memorized in advance, then performance is going to increase as a function of the number of tasks that you've memorized. So it's basically going to increase as the training data size increases and the parameter count increases. And my take on intelligence is that you cannot reduce it to just memorizing every possible task, every possible situation that you might encounter, right? So if you want to really think about intelligence, try to rigorously define it, try to measure it, here are three key concepts that you have to take into account. So the first thing to keep in mind is the distinction between static skills and fluid intelligence. So between having access to a collection of static programs to solve known problems versus being able to synthesize brand new programs on the fly to face a problem you've never seen before. And of course, it's not one or the other. There's a spectrum between the two. But intelligence is on the side of fluidity. And the second concept is operational area of the skill programs you have. There's a big difference between being skilled only in situations that are very close to what you're familiar with and being skilled in any situation within a broad scope. So for instance, if you know how to add two numbers, then you should be able to add any two numbers, not just numbers that are close to numbers you've seen before. Or if you know how to drive a car, then you should be able to drive in any city, not just in one specific geofenced area. And the last concept you should look at is information efficiency. How much information, how much data was necessary for your system to acquire a new skill program? And of course, higher information efficiency means higher intelligence. So one big takeaway I want you to remember, there's just one thing you remember from this presentation, is that skill is not intelligence. They're actually entirely separate concepts. And you can always display skill at any number of tasks without having any intelligence. In the limit, the only thing you need is a big lookup table that tells you how to respond to any given situation. And so the difference between skill and intelligence is kind of like the difference between a road network and a road building company. Intelligence is a process, and skill programs are the output of that process. The same way that a road network is, an artifact that was created by this road building company. If you just have the road network, then you can go from A to B for a specific set of A's and B's. But if you have the road building company, then you can start connecting arbitrary A's and B's on the fly as your needs evolve. So you shouldn't go attribute intelligence to a crystallized behavioral program, a crystallized skill program. That would be a category error. You would be confusing the process and its output. Intelligence is really the ability to deal with new problems, new situations. It's the ability to create new roads. So don't confuse the road and the process that created it. And personally, I want to make more intelligent machines. I want to make machines that have the ability to turn data into models on their own and do so efficiently. And one really important thing to understand about model building ability is that it's a spectrum. It's a spectrum of abstraction that goes from weak abstraction and weak generalization to strong abstraction and thus high intelligence. So a spectrum from factoids to organized knowledge to abstract models that can generalize broadly and accurately to finally meta models that enables you to generate new models on the fly to fit a given situation. And the degree 0 of that spectrum is when you're purely memorizing pointwise factoids. There's no abstraction involved. That's not going to generalize at all past what you've previously memorized. So here you have 3 factoids, and I chose to represent them as functions. And they're functions that do not take any argument, which is how you know that they're not abstract. And once you start having lots of related factoids, you can try to organize them into abstract functions that encode knowledge. So here you have such a program that represents organized knowledge, and you can tell it's abstract because it takes one variable. So it is abstract for X. And the deep learning paradigm, curve fitting, is actually really good at this kind of knowledge organization, where you take pointwise factoids, you embed them on a curve, and then you can start interpolating between them. But the problem with this type of organized knowledge based on pointwise factoids and interpolating between pointwise factoids is that it's not actually going to generalize very well. It looks like abstraction, but it's relatively weak abstraction. It might be inaccurate. It might not work on data points that are far from what you've seen before. And the next degree after that is to turn your knowledge into abstract models. So a model doesn't encode factoids anymore. It doesn't encode interpolation between factoids. Instead, it encodes a concise way of processing your inputs to obtain the desired result. So here, for instance, you have a model of addition, and it's an algorithm expressed in terms of binary operators. So it's the kind of algorithm that you might find if you're running a program search process, a program synthesis process on a few examples of addition. And a model like this is going to generalize strongly. So it will be able to return the exactly right answer, not just an approximate answer. It's not going to be accurate, 80% or 90% of the time. It's going to be accurate 100% of the time. And it's going to work for any input, even inputs that are very far from the distribution of inputs that you looked at to come up with the algorithm. So that is strong abstraction. And that is where LLMs today still fall short. And the next stage after that is the ability to generate models like this autonomously. And this is how you're going to be able to handle novel problems, stuff you've not been prepared for. And this is what intelligence is, as opposed to just knowledge or crystallized skills. And the very last stage is to be able to do so, come up with new models on the fly in a way that is maximally information efficient. So that means that you should be able to master new tasks using very little experience, very little information about the task. And not only are you going to display high skill at the task, meaning that the model you've created can generalize strongly, but you will only have to look at a few examples, a few situations to produce that model. And by my definition, this is AGI, and today we're pretty far from it. So how far exactly? Well, if you want to situate LLMs on this spectrum of abstraction, they're going to be basically at the organized knowledge stage. You can tell they're not quite at the model stage, because if they were at the model stage, then you could actually add numbers with LLMs reliably or solve Alice in Wonderland problems for any values of n and m. But they do actually have a lot of knowledge, and that knowledge is highly compressed, highly structured in such a way that it can, in fact, generalize to some distance from previous situations. LLMs do generalize. They do make sense of some amount of novelty. They are not just a lookup table of lots of pointwise factoids. And this is exactly what makes them useful. And if we were to solve all the problems we have with LLMs today, like the hallucinations, the patchy generalization, and so on, you would get one stage ahead. You would get at the model stage. You would have reliable models that can generalize strongly. And this will be tremendously valuable, obviously. This will be many billions of dollars of value. But if you want to get to the next stage, to autonomous model generation, you will still need another massive jump. You cannot purely scale the current approach and get there. You have to change direction. And after that, AGI itself is still a pretty long way off. So concretely, how do we make machines that can autonomously produce their own models on the fly? My answer is abstraction. I think abstraction is the engine of modeling. It's the engine of generalization. Abstraction is the process through which you turn observations into models. And at the high level, abstraction is all about analogy making. Abstraction is sensitivity to analogies. So if you have a high sensitivity to analogies, you will be able to extract powerful abstractions from your past experience, and you will be able to use these abstractions to operate in a maximally large area of your future experience space. So you will be intelligent. And importantly, there's more than one way to draw analogies. I think there are exactly two ways, and this is really important. I think there are two key categories of analogies from which arise two categories of abstraction. There's value-centric abstraction and program-centric abstraction. And they're pretty similar to each other. They mirror each other. So both are about comparing things and merging individual instances into common abstractions by eliminating certain details about the instances. So you take a bunch of things, you compare them, you drop the details that don't matter, and what you're left with is an abstraction. And the key difference between the two types is that one operates over a continuous domain and the other operates over a discrete domain. So value-centric abstraction is about comparing things via a continuous distance function. So you take two things and you're asking, so how similar are they in terms of degree of similarity? And this is the kind of abstraction that powers human perception, intuition, pattern recognition in general. And on the other side, program-centric abstraction is about comparing discrete programs, which is to say graphs. And instead of asking, how similar are these two programs, instead of computing distances, what you're going to be looking for is exact subgraph isomorphisms. You're looking for similarity at the structure level. You're looking for exact structural matches. And this is what powers human reasoning. It's also what software engineers do. Like if you hear a software engineer talk about abstraction, they're talking about this. Like how do you refactor two functions into one abstract function? You are looking for an exact subgraph isomorphism. So two forms of abstraction, both driven by analogy making. You have value analogy on one side, which is geometrically grounded. You're comparing instances with a distance function. And you also have program analogy, which is topologically grounded. You're comparing the structure of two graphs. And I really believe all cognition, all intelligence arises from a combination of these two kinds of abstraction. And one way to remember them is you had a left brain versus right brain metaphor, with one half for perception, intuition, one half for reasoning, planning, and so on. And I really think transformers are great at type 1 abstraction. They can do everything that type 1 is good for, perception, pattern recognition. So in that sense, they represent a major breakthrough towards AGI, but they're not yet a good fit for type 2 abstraction. And this is where all the limitations that you know about come from. This is why you cannot add numbers reliably with a transformer, even if it's trained on millions of examples of addition. So how do you get to type 2? How do you move forward? Well, my answer is that you have to leverage discrete program search as opposed to just curve fitting. And that is an entirely separate branch of computer science compared to modern machine learning. And we have to merge it with modern machine learning in order to get to general AI. So if you're not familiar with it, what is discrete program search? Well, it's simple. It's basically combinatorial search over graphs of operators taken from some language. something that you would call a DSL, a domain-specific language. And to better understand program search, you can try to make an analogy between machine learning and program search. So in machine learning, your model, the thing you're building, is a curve. So it's a differentiable parametric function. In program synthesis, your model is a graph of ops taken from a DSL. In machine learning, your learning engine, how you make new models, is gradient descent. And in program synthesis, it's going to be combinatorial search. In machine learning, the key obstacle that you run into is that to fit a curve, you need a ton of data. You need a dense sampling of the problem manifold. And program synthesis is very different. Program synthesis is actually very data efficient. You can learn a new program using just a few data points. But in order to do this, you have to look at many different programs. The key challenge that you run into is combinatorial explosion. The size of the program space you have to search over is going to grow combinatorially with the size of the DSL and also with problem complexity. So you can use program synthesis to solve problems from very few examples, but you have this compute issue, this combinatorial explosion wall that you run into. And back in 2020, when I launched the first edition of the ARC competition on Kaggle, my initial prediction was that all the winning entries were going to be using program synthesis, because I saw ArcAGI as a program synthesis benchmark. And as a matter of fact, that's exactly what happened. They all did. And the winner scored at the time 19% using a very basic brute force program search technique. And today, somewhat more refined versions of this technique can do up to roughly 40%. But we know that at least 50% is feasible with nothing more than brute force program search, with basically no intelligence at all. We know this because 50% is what you get if you ensemble all the submissions from 2020, right? And until basically this week, this was actually state of the art, right? And meanwhile, LLM-based approaches, they've only started taking off this year. So in previous year, you had GPT-3, which scored basically 0 on ARC. And today you have O1, you have Claude 3.5 Sonnet, they score about 21% on the public leaderboard. So big progress there. And today the top entries on both the public and private leaderboard, they're not pure LLMs, they're not pure program search, they're a combination of LLMs in some kind of search style recombination, either actual program search or test time fine-tuning. And so that gets you to somewhere between 40 to 50%. So you know that discrete program search has proven to be a very powerful tool to approach ArcAGI or any kind of reasoning problem, really. And meanwhile, LLMs are also starting to show very strong results. So where do we go next? Well, I said earlier that I believe all cognition is a combination of two forms of abstraction, of type 1 and type 2. And I really don't think that you can go very far with just one of those. You have to combine them in order to achieve their true potential. And I think that's what human intelligence is really good at. That's what makes humans special. We combine perception and intuition together with explicit step-by-step reasoning. So we combine both forms of abstraction. Like if you're playing chess, for instance, you're using type 2 when you're calculating, when you're unfolding some potential moves in your head step by step, but you're not going to be doing this for every possible move because there are way too many of them. So you're only going to be doing it for a couple of different options. And the way you narrow down these options is via intuition. You just look at the board and you see where the good moves are. So this is basically pattern recognition that you're building up through thousands of games, through extensive experience, and that is very much type 1. So you're using type 1 pattern recognition to make type 2 calculation tractable. So in an AI system, how would you create the same thing? Well, the key system 2 technique is discrete search over a space of programs, and the blocker you run into is combinatorial explosion. And meanwhile, the key system 1 technique is curve fitting and interpolation, right? So you take a lot of data, you embed it on a manifold, an interpolating manifold, which enables fast but approximate judgment calls about the structure of the target space. And the big idea to combine the two is going to be to leverage those fast but approximate judgment calls to fight combinatorial explosion. So you use them as a form of intuition about the structure of the program space that you're trying to search over to make search tractable. A simple analogy to understand this is drawing a map. So when you're drawing a map, what are you doing? You are taking a number of discrete objects with discrete relationships that would normally require combinatorial search, like pathfinding is a pretty good example. Pathfinding is a combinatorial problem. And you are embedding these objects on a geometric manifold where you can use a continuous distance function to make fast but approximate guesses about the discrete relationships that you're interested in, things like passes, directions, and so on. And so this enables you to keep combinatorial explosion in check. So today, I think there are two exciting research areas to combine the strength of deep learning and the strength of program synthesis. So first, you can start building models that will incorporate discrete programs and deep learning components. Like for instance, you can use deep learning as a perception layer to parse situations into discrete building blocks that you can then feed to a program synthesis engine. Or the other way around, you can add symbolic add-ons to a deep learning model, what's known as tool use nowadays. And the other direction is to make deep learning models that inform discrete search to improve its efficiency. So you're going to use deep learning as a driver, as a guide for program synthesis. It's going to give you intuitive program sketches to guide your search. It's going to reduce the space of possible branching decisions you have to look at each node. So in the context of ArcAGI, what does this look like? So this is the part where you should be paying attention, because I'm going to spell out to you how you can crack ArcAGI and win the $1 million. So there are two directions you can go. The first direction is that you can use deep learning to draw a map of state space, of grid space, right? So you're going to learn a manifold that embeds grids, and where the distance between 2 points, between two grids, approximates the number of discrete transformations that you have to make to go from one grid to the other. And in the limit, this solves program synthesis. Because if you have a new task, let's say you have an input and an output, well, you take your input grid, you embed it on the manifold. You do the same with the output grid. And now what you're going to do is just draw a line between the input embedding and the output embedding. Draw a line along the manifold, and then look at the points that the line interpolates. They decode back into grids. And now what you have is basically a guess as to what series of grids, what series of transformations on your grids maps the input to the output. So you're turning program synthesis into an interpolation problem. And of course, this is a guess, this is an approximate process. You're still going to need to do some amount of discrete search to find an exactly correct program. This dramatically reduces the amount of search that you have to do. And the other direction you can go is program embedding. You can use deep learning to draw a map of program space this time. And then you can use this map to make your discrete program search more efficient. And right now, we've only really started scratching the surface in terms of exploring these ideas. I strongly believe that we're about to crack ArcAGI. Like within a couple of years, this will be solved at human level, and we are going to move on to the next benchmark. And the solution is going to be built directly on top of these ideas. And maybe it will be built by one of you. And that's the reason why we are doing this presentation, is that we want to reach the person who's going to tackle this problem and crack it. So now I'm going to hand it back over to Mike, and Mike will tell you how you can get involved with ArcPrize today. Thank you.
All right. Thanks, Francois. So yeah, we are on tour. The reason we spent all October basically going on tour to all these different universities and doing this event is we want to try and hopefully reach the person who's going to finally crack this thing. While there's been a lot of progress this year so far, we think we still need new conceptual progress to get to beating the grand prize. I think sort of probably current approaches could scale a little bit further, but we really do need some sort of new unlocks to get there. And we think it's likely to come from an outsider. We think that these sort of new ideas are probably most likely going to come from merging together, like sort of different backgrounds, different fields together. And it's unlikely to come from, just training, big lab, training the next, billion parameter, trillion parameter sort of sized model with more and more data. In fact, so our own personal belief is that ARC will likely get beaten, with like a 7 billion parameter model or less and like 10,000 lines of code or less. And if that's true, then I think that puts it in the hands within the reach of like individual teams, very, very small labs, very small budgets, which is pretty exciting, I think. And yeah, we're here because maybe one of you on the stream today will be the one to get inspired and figure out how to beat this thing. So ArcPrize 2024 is running right now. There's 17 days left until the end of the contest on November 10th. If this is the first time you're hearing about it, I wouldn't worry too much though, because we don't expect anyone is sort of going to come out of the blue and sort of win the grand prize this year. And so here's what we're going to do about it. We're going to be running this contest annually every single year until someone can finally crack this thing and beat it. And in the meantime, we're going to have progress prizes. So this year we've got 2 main progress prize categories. We've got this 50K set aside for the top scorers, the top performing teams this year. These are going to get paid out no matter what. And then we also have a new thing, this paper award. So we put 75K into a paper award. Basically, whoever submits a paper by November 10th that points at an approach, it does not need to be a winning approach. It can actually be sort of a very performing approach, but moves conceptual progress forward the most, judged by like a rubric that we have published on the website that France Wyron are going to judge. There's going to be a 75K progress prize for that. And again, we're going to pay those out sort of no matter what. And the goal is or the hope is that we're going to get a lot of new ideas, conceptual progress, and open source code from ArcPrize 2024. One of the sort of criteria of getting any of the prize money on the progress side, you have to open source and put your sort of progress into public domain. And hopefully we'll then use downtime over the winter months here to sort of re-baseline the entire community working on ArcPrize so that everyone can sort of be like operating at state of the art going into next year. We're going to be announcing all the winners in early December, and then we are going to be at NeurIPS this year. Actually, we're going to be speaking at the System 2 reasoning workshop. It's on the weekend, on Sunday. And there we're going to be announcing all of the new open source like code, basically. Like here's all the new approaches, here's what teams were doing, here's what's working, here's what people tried, and here's a way that you can go actually reproduce that stuff yourself. So if you're going to be at NeurIPS, we'll be excited to see you there, and you can come say hi on Sunday at that workshop. And then we also have a public leaderboard. Most of what we've talked about so far today on the prize, private side is on the private leaderboard with the prize money. We also have a public leaderboard, and this is a great way, I think, to get started in ArcPrize. If you're just hearing about it for the first time, you want to get your feet wet. The public leaderboard lets you use commercial models, so things like O1 or Claude. And while there's no, like I said, prize money for this track, we do have 150K set aside for reimbursement as a reimbursement fund to sort of verify high scores on that. And so it's just a really easy way to get started. There's actually open source approaches on the leaderboard right now that you can go like run yourself on Kaggle and get some pretty good scores to get started there, including Ryan's we mentioned before. If you're wanting to get started, go to the website, arcprize.org. There is details on the full competition and a really, really good technical guide by Greg, who kicked us off this morning. He wrote this really fantastic resource that has an overview of like all the different data sets, distinguish the sort of differences between all the data sets, links to a lot of past approaches, defining a lot of terms, just like a really, really good technical guide if you're thinking about getting started with it. Then we also have, like, of course, Discord, really good community there engaged on it and sharing ideas, an email list as well. We're sharing out updates. And then, of course, one of my favorites, the ArcPrize Twitter account, where probably like once, twice a week, we're sharing out like frontier papers, either in deep learning, discrete program search, program synthesis, that we sort of wish some team, somebody would try applying to Arc to see if it could work. And so if you're kind of wanting to work on Arc, but you're not inspired yet on a certain approach, follow that Twitter account. It's a really, really good one. And of course, we're also tweeting out every progress percentage point as we get closer and closer to the grand prize. Okay, I think that's it for our main content today. We're going to switch over here to Q&A. You can ask us about the contest. You can debate the premise. You can ask us on solution paths, whatever is interesting. We got the QR code here, the links on the website as well for the Dory, which we'll use to sort of moderate the QA and Q&A. And I'll hand over, I think, to Brian, who's going to, on the ArcPrize team, is going to help us moderate.
Thank you, Mike. Thank you, Francois, for your talks. As Mike mentioned, looks like we don't see the QR code, but if you go to arcprize.org/tour, you can see the link to upvote questions and ask your own. There it is. There's a code you can scan as well. So I will route your questions to Mike and Francois. We're going to kick it off with Francois. So here we go. What inspired, this question's from Eduardo, by the way. What inspired the core knowledge priors in your paper on the measure of intelligence? And do you still stand by those? Would you consider adding or revisiting any of them, for future versions of the benchmark?
Right. So the benchmark was really focused on skill acquisition, which should be, in my opinion, independent from knowledge. But in order to acquire skills, you do need some knowledge, some base knowledge that you're starting from. So you need to decide, here's what you need to know, right? And every benchmark out there, including all the exam style benchmarks that we use for LLMs, they all require some knowledge. But most of the time that knowledge is actually implicit. It is necessary, but you don't know what kind of knowledge is necessary, right? And the difference with ARC is that ARC actually makes it explicit. It tells you, here's the core knowledge system that you're going to need. And so why pick core knowledge as opposed to, I don't know, programming or anything like that? The reason is that I wanted to make it possible to compare machine intelligence and human intelligence. And so you have to standardize on some set of knowledge, some kind of knowledge priors. The natural thing to standardize on is the prior knowledge that is universally shared among all humans, including even fairly young children. So that's the motivation behind core knowledge, is that you're going to need some foundation to build on. You're going to make it explicit. You're going to make it simple, right? And you're going to make sure that it is something that puts humans and machines on a fair ground.
Very good. Thank you, Francois. All right, this question's for Mike from Myson. What is the most innovative approach to ArcAGI you have seen thus far? Maybe at the top of the leaderboard?
Yeah, so we talked about Brian's approach on the public leaderboard during the slides, right? This like generating lots of Python programs. I think it's kind of interesting to contrast that approach with the approach Minds AI is taking from this is, what we've heard from them that they've said publicly. Obviously, we don't have like insight into their code yet. But from talking with them and understanding what they've shared, basically they're doing something called test time fine tuning, right? Where they're using a very small open source code gen model, like a 200 million parameter model, pre-trained on code, and then pre-training it on like puzzles that look like the ARC public set, using, I believe, the sort of Michael Hodel DSL that's on GitHub, and using that to generalize synthetic data to do this pre-train. And then what's interesting about it is it doesn't do very well, right? It only gets maybe a few percentage of the puzzles right with just a single pre-train. And so in order to get the like really impressive progress they've made inside the Kaggle runtime, basically they're doing test time fine tuning, where in exposure to the private data set, the private puzzles, they generate additional synthetic versions of those using the DSL, and then do a fine tune of that same underlying model, and then doing a sort of JSON in to JSON out inference prompt of it. I'm sure to get to the sort of 50% that they just cracked, there's a lot more bells and whistles, but I think that's like the general thrust of the approach, is this like idea of test time fine tuning. And what's maybe most important about it is that like it has a way now, that system has a way to conceptually make contact with reality, right? Make contact with like a new situation it's never seen before, and incorporate some element of that back into the underlying distribution, right? Into the underlying model that it uses to sort of go after additional puzzles. And this is in contrast to, say, a large language model like O1, where, while they are doing search at test time, they're not able to like make contact with reality and incorporate new information that it's discovered back into the underlying fine tune. In fact, I actually think that like alpha proofs, our DeepMind's alpha proof system is like one of the coolest systems that exists today. And they do both of these things. They have both a inference time search mechanism looking over like lean math theorem programs to solve these like IMO challenge questions. And they have a test time fine tune loop running as well. When they discover new math theorems or partial theorems, they like bake it back into the underlying distribution. So really, really cool approach that they're doing as well. And yeah, I think probably the sort of top two approaches in leaderboards are probably the most sort of intellectually interesting right now.
That's amazing. Sounds like the competition is working. Excellent. All right, this question is for Francois from Tony. Do you think the wrong approach will beat the 85% mark first? Wrong meaning not generalizable, highly targeted toward the data set, brute force. And if so, do you plan on revisiting the data set to make it harder for these approaches?
Yes. So we already know that the ArcGI benchmark has flaws. It was an initial attempt at creating a benchmark for skill acquisition efficiency, but the first attempt was obviously not perfect. So for instance, the fact that we know we can solve about half of the private test set using just brute force program search is a flaw, right? And so we're going to keep iterating. So next year, for the 2025 edition, we're going to have a brand new data set. And it's a data set that will be more interesting. It is intended to be higher signal in terms of the way it measures intelligence. So it's not going to be harder for humans. The tasks are going to be just as hard, meaning very straightforward, as the ones in ARC 1, but they're going to be less brute forceable. And we don't know yet whether the first approach that will crack 85% is going to be interesting and useful and generalizable, or whether it's just going to be some kind of shortcut. It is often the case that benchmarks fall to shortcut style approaches. I was, of course, very, very much aware of that when I designed ARC. I did my best to prevent that. I did my best to create something such that if you can crack it, we will need to have learned something about the nature of generalization, about how to acquire new skills, solve new problems on the fly without having been prepared for it. And I do believe that whatever we build, we'll be able to learn something from it, and that something will generalize to new domains. So for instance, if you just figure out a really efficient way to do program search, even if it's mostly based on brute force, by just swapping out the DSL or making it so that you can learn the DSL for a new domain, then you can move that program search approach to a brand new domain. You can start solving mathematics, for instance. You can start solving all kinds of things.
Excellent. Very good. Mike, this one's for you. A lot of questions about the future of ArcPrize today. So this is exciting. From Guillermo, who is actually number 3 on the Kaggle competition right now. So shout out to Guillermo. Have you considered creating research grants for people to keep working to solve ARC challenge when the 2024 competition is over?
We thought a lot about figuring out how, like, the ultimate goal here is to figure out how to beat this thing. I think there's a lot of different like market shaping mechanisms you can use to try and direct attention and progress. The main challenge we were really trying to solve coming into the contest period this year was awareness. Awareness was just really, really low. So, we put, thousands of hours probably collectively into the website, into all the launch material, into getting the design of the contest really good. Again, largely to sort of solve our, and at this point, I think we've actually cracked the awareness problem. I think most probably people in the AI industry are at least peripherally aware of the fact that ARC and ArcPrize exist now. And so we're kind of entering a bit of a different, like a phase shift as we move forward, which is like, okay, how do we move conceptual progress forward the most? And, I think to Francois's point, I don't think any one of us believe that like V1 of the data set is like perfect. I think our sort of long-term mission here is to figure out how do we continue to make ArcPrize sort of the best sort of compass or North Star to point towards AGI, and always try to be a sort of like pointer to like, what are the things that, humans can do that computers can't yet, and figure out how do we benchmark that and actually be a capability assessment for it. So I think research grants are sort of an interesting option. I think the main thing we've like committed to so far is we're going to keep running the contest. We know we're going to keep running the contest annually until we can at least get this form of this first benchmark beaten. But yeah, I think we're always exploring sort of ideas of like, how do we actually move conceptual progress forward the most? And certainly something like this is on the table, but nothing to like announce or share yet at this point.
Excellent. All right, we're going to do one last question before I turn it back to Mike to close us out today. Thank you, everybody, for joining on X, on the Restream. It's great to see you.
Are we going to do anything with the extra Q&A stuff? We should.
Yeah. You know what? Let's keep the dory open, and people can continue to add questions, and we will follow up with.
Maybe we can like drip out answers over like the ArcPrize Twitter account throughout like the rest of the day or something. That'd be like a fun thing to do.
There you go. It shall be so. So, Francois, last question for you. No Q&A would be complete without this one. We've heard some version of this at every university event we were at. Constantly hearing, what is your response to people who say ArcAGI is easy for humans and hard for LLMs because of the visual nature of the benchmark?
Right. So the main thing to understand is that ArcAGI is not a visual reasoning benchmark. It is a reasoning benchmark over grids, 2D grids of discrete symbols, which is very, very different from a 2D grid of pixels because you have no notion of local similarity. And if you take a transformer, let's say you take an LLM, for instance, it's very easy to train it on many instances of a single task. So for instance, there's a repo on GitHub created by Michael Hodel that it's basically made it possible to generate more instances for certain tasks that is programmed. Well, you can generate a bunch of instances for a task and then fit an LLM on it, and you will see that the model fits perfectly well. It is able to learn a program that solves the task that will generalize to new instances. So that tells you that there is no issue with tokenization. Tokenization works fine. There is no issue with representing the solution program when you take as input a flattened representation of the grids. It works. The only issue where LLMs are not able to solve ArcAGI is unfamiliarity, the fact that the problems are narrow. We've also seen that by adding vision to these models, by starting to use vision language models, you are not getting any sort of performance boost. If the big blocker was the lack of access to this visual component, then adding the visual component, and nowadays vision language models are becoming completely mainstream. There's a bunch of open source already. You can play with them. There are also a bunch that are available via black box APIs. This is not making any difference. The best performing models today do not have any sort of vision component, right? And lastly, one note is that you have to remember that transformers are not sequence processing models, unlike what many people believe. If you look at the architecture, they are actually set processing models. They are computing the entire matrix of pairwise token interactions, right? So a transformer is a model for processing a set of discrete tokens with arbitrary structure. And the way you will add awareness of sequence ordering is by adding a position embedding. So it's actually at the feature level, right? But what you're doing with position embeddings, you could do it with, for instance, a 2D position embedding. You could add to your transformer awareness of the 2D structure of the grid. And then you have a kind of model that is architecturally able to natively process arc grids. And you can try that. And you do see actually that there's some improvement over the pure sequence style transformer. But again, it's not going to solve the problem because the problem is not representability or tokenization or any sort of input. The input part works just fine. The problem is the novelty element, the fact that you have to fit a program that is not in your memory, that you've not seen before. You have to figure it out on the fly. And so far, the only technique that seems to work well to fit this program is what MindSI is doing with test time fine-tuning. And the fact that it works so well kind of tells you that the major bottleneck, the key that we are missing is recombination. Test time recombination is that you have a bunch of knowledge in your model, but just fetching that knowledge and trying to blindly apply it to a new problem is not going to work because the new problem is novel. You have to actually recombine it into a brand new model that is adapted to your new problem. Test time fine-tuning does that. It uses gradient descent in this case to do it, which I think might not be optimal. But it's also what program search is doing. In program search, your knowledge is your DSL. And at test time, you're trying many different combinations to find one that models the task at hand. So you need this recombination step. That's what you're missing. You're not missing anything at the input level.
All right. Hopefully that inspired you all to come up with some new solutions in the closing days of this year's competition. Before I turn it over to Mike to close us out, I just wanted to say thank you on behalf of me and Greg, the co-leads of ArcPrize. Thank you to all the students and faculty who are so brilliant, who came and hung out with us at all of our university stops, and especially the student organization leaders and the staff who made it possible for us to visit these wonderful schools. And with that, I'll turn it over to Mike.
Yeah, super big thank you. I think we had a few thousand people actually like hanging out with us today and watching this. So hopefully picked up some ideas of how you can go beat ArcPrize yourself. There are 17 days left in the 2024 contest. So if you're working on it, top score, good luck. If you're just getting started, maybe consider the paper track for this year. Still time to sort of make some conceptual progress towards this thing. And yeah, like I said, we'll sort of organize all the Q&A that we didn't get to today. I was just scrolling through. There's some really good questions in here. So we'll try to organize maybe group-like ones together, and we'll like tweet answers out from the ArcPrize account today. So if we didn't get to your question, thank you for submitting them, and look for the Twitter account answers as we go throughout the rest of the day today. All right, we'll wrap there. Hope to see everybody on the ArcPrize leaderboard. Have a great day.